Let's discuss how sodium affects the extracellular fluid compartment. We will use yellow dots to represent our sodium concentration. Remember that the extracellular compartment, meaning the intravascular and interstitial spaces, remain in osmotic equilibrium. For our purposes, we'll combine them here. We also know that the sodium is the most abundant solute in the extracellular compartment, with an average concentration of 140 milliequivalents per liter, compared to 10 milliequivalents per liter in the intracellular compartment. The yellow dots serve to represent the sodium concentration differences. In a static state, meaning without the addition of solute or water to the system, due to other competing osmotic and oncotic properties intra and extracellularly, the two spaces remain within osmotic and oncotic equilibrium, as indicated by the small black dots. Going forward, we will remove the black dots for simplification and focus only on the sodium. Finally, recall the cell membrane is a semipermeable membrane that allows water to move freely between the intracellular and extracellular compartments, whereas molecules like sodium cannot move freely across the membrane. Therefore, sodium can exert an osmotic effect across a membrane, where water moves from lower to higher concentrations until osmotic equilibrium is reached. For these reasons, sodium is the most important determinant of extracellular volume. Now, let's explore the impact of a solute load on extracellular volume. This example is not physiologically accurate, but used to simplify a concept, so assume this is a closed system. We'll maintain that the intracellular compartment volume is twice that of the extracellular compartment volume, as was illustrated in the previous water distribution model. At this point in time, the compartments exist in equilibrium. Let's add sodium to the extracellular compartment and increase the sodium mass by 10%, which, as we already know, this will exert an osmotic force where water moves into the extracellular compartment until equilibrium is again reached. In this example, we observe a 10% increase in sodium mass within the extracellular compartment. The extracellular compartment will therefore gain volume, while the intracellular compartment will lose volume. Remember, the intracellular compartment is twice that of the extracellular compartment. Therefore, the volume gained in the extracellular compartment is proportionally twice the volume lost from the intracellular compartment. To put numbers to this, the extracellular compartment would expand 6.7%, and the intracellular compartment would shrink 3.3%. This example reiterates the crucial concept that sodium is the most important determinant of extracellular volume, most specifically intravascular volume. Therefore, the maintenance of sodium balance determines mean arterial pressure and left ventricular filling pressures. One can imagine inability to regulate sodium balance threatens the existence of an organism. Let's review how various intravenous infusions will impact our intracellular and extracellular compartments. We'll focus on isotonic crystalloid, D5W, and plasma. Isotonic crystalloid refers to intravenous fluids like lactated ringers or 0.9% normal saline. These fluids are frequently used in volume depletion or shock in an attempt to return blood pressure to normal. Sodium concentration in isotonic crystalloid solutions are similar to or slightly higher than the serum sodium concentration of plasma. The addition of 2 liters of isotonic crystalloid to the intravenous space will be distributed evenly throughout the extracellular compartment. Based on normal distribution, 1/4 of the infusion, or 500 milliliters, will go into the intravascular space, and 3/4 of the infusion, or 1,500 milliliters, into the interstitial space. Water from the intracellular compartment will move into the extracellular compartment until osmotic equilibrium is reached. Dextrose 5% in water, annotated D5W, is the intravenous form of free water. Dextrose accompanies free water in intravenous form to prevent cellular lysis with free water alone. Administering water intravenously in the form of D5W will have a greatest effect on the intracellular volume. which is twice that of the extracellular volume. Here, 2/3, or 1,340 milliliters, will distribute intracellularly, and only 160 milliliters, or 8%, will distribute into the intravascular space. Plasma is a component of blood devoid of blood cells. It is made of 95% water and contains all important dissolved proteins, electrolytes, clotting factors, enzymes, hormones, immunoglobulins, carbon dioxide, and oxygen. Plasma infusion will expand the intravascular space most effectively since its larger components like dissolved proteins, like albumin, enzymes, clotting factors, and immunoglobulins, cannot readily traverse the endothelium. Water from the intracellular compartment will follow osmotic and oncotic forces and move into the extracellular compartment until equilibrium is reached.